In part 2 of our review on general chemistry, we're going to look at stuff like drawing Lewis structures and analyzing their geometry and bond angles and all that good stuff. So just a reminder on when you draw appropriate Lewis structures, you want to first calculate the number of total valence electrons. So in something like CH4, which is formerly named carbon tetrachloride, we'll later see that it's more often called methane. Carbon is in group 4A, and so it has 4 valence electrons. Hydrogen is in group 1A, so it has 1 valence electron, but there's 4 hydrogens. So your total that you would calculate would be 8 valence electrons that you have to place in your Lewis structure. And so your carbon would be your central atom, and then you would have your outer atoms surrounding your central atom. And then you at least have to connect with a single bond your outer atoms to your central atom. And so when we do that, we use up 2 electrons. So that's 2 electrons, 4, 6, and 8. And so in this example, there's no leftover electrons, so we don't have to worry about anything else. That would be our Lewis structure for CH4. Now let's do that for H2O, for water. So hydrogen has 2 valence electrons, or 1 valence electron times 2 hydrogens, so 2 total. And then oxygen's in group 6A, so we have 8 electrons total to place. Our oxygen is going to be our central atom. Hydrogen is never a central atom, if you remember, so it's going to be on the outside. And then we're going to connect with 2 electrons to the central atom, so that uses up 4. So we have 4 electrons left over to place now. And when you run out of essentially atoms to put them to, you have to put them as lone pairs on the central atom. So they go together as a pair, so you're going to have 1 lone pair here on the oxygen, and you're going to have another lone pair here on the oxygen. So in this example, we have 2 lone pairs of electrons on that oxygen that become very important in knowing that they're there when looking at chemical reactions. Let's try a couple more examples. We have SO3, sulfur trioxide. So sulfur and oxygen are both in group 6A, so that's going to give us a total of 24 valence electrons. So when we start our skeleton structure, we're going to put sulfur in the middle, surrounded by the 3 oxygen atoms. We're going to connect with single bonds, so that it uses 2, 4, 6 electrons. And now we're going to complete the outer octets, because oxygen does not have a complete octet yet. So we're going to go 8, 10, 12, 14, 16, 18, 20, 22, 24. So it took all 24 electrons to complete all the outer octets. But notice our sulfur does not have a complete octet. It only has 6 electrons around it. So this is where we have to create a multiple bond. We're going to take any of the lone pairs on, pick any oxygen atom, and move it over to create a double bond. And then that will make sulfur think that it has a complete octet. So our final structure would look something like this. Where we have 2 single bonds and 1 double bond. But in reality, the real structure of SO3 is a hybrid structure where it's not exactly, the bonds aren't different, they are a combination of the double and the single bond. But for drawing a Lewis structure, that's appropriate. And let's do an ion now. So we have NO3 minus, the nitrate ion. Our total number of valence electrons we have to place is 24. Just a reminder, when you have a negative charge, you add an electron for that negative charge. If you had a cation, you would subtract for a positive charge when calculating the total valence electrons. So for nitrate, we're going to put our nitrogen in the middle, surround it by our 3 oxygens, complete the skeleton structure, so that uses 6 electrons, and then we would have our complete octets on all of our oxygen atoms. And just like last time, we have a situation where nitrogen does not yet have 8 valence electrons around it, so we can pick any lone pair and move it over and make a double bond. So our Lewis structure will be 1 double bond to an oxygen with 2 lone pairs on that oxygen, and the other 2 oxygens will have 3 lone pairs. One other thing about ions is when you represent their Lewis structure, you put brackets around them and then you write the charge on the outside so that when we look at it, we know that there's an overall charge to that species. So since nitrate is a -1, we throw a -1 on the outside of the brackets. I also want to remind you that after you draw a Lewis structure and you draw the correct structure, you can assess it and determine if the molecule is polar or nonpolar. Polar molecules are molecules that have asymmetry. They are asymmetrical in some way, shape, or form. It could be because of their shape, or it could be because they have a different outer atom compared to the others. Molecules that are nonpolar are going to be symmetrical. So that's kind of the simplest way to think about it. So if we look at the examples below, we have CHCl3, which is chloroform. And if we had 4 chloro groups on the outside, it would be tetrahedral shaped, and therefore it would be totally symmetrical, and it would have no net dipole, meaning it would be nonpolar. But once you've substituted one of the outer atoms and changed it, now it has a net dipole towards the more electronegative chloro groups. So overall, this is a polar molecule. Same thing with the two on the right. Water and ammonia are both polar molecules. Usually, the asymmetry in a molecule will be a result of a lone pair of electrons on the central atom. So we just drew the Lewis structure for water, and even though they're not shown here, we know that there's 2 lone pairs of electrons that are on that oxygen atom. So that leads towards a net dipole heading towards those electronegative lone pairs. So the net dipole is in this direction, but it's a polar molecule because of that asymmetry in its shape. Same thing with ammonia, NH3. There's actually a lone pair of electrons on the nitrogen, and so that shape is asymmetrical due to those lone pairs, and it leads to a net dipole in that direction towards the lone pair. So this is also an example of a polar molecule. Usually what we use is VSEPR, which is a theory that allows us to predict the shape of the molecule, the bond angles, and it tells us a little bit about the polarity too. So we can use that VSEPR theory and if it's symmetrical or asymmetrical in order to figure out if the molecule is going to be polar or nonpolar. 2 examples of shapes that you would have seen before that are actually nonpolar but do contain lone pairs of electrons are these 2 exceptions. So on the left-hand side, we have a linear molecule, but it would have been AX2E3, where you actually have 3 lone pairs of electrons that are in the equatorial plane. And so those lone pairs actually end up canceling each other out. And as long as the 2 outer atoms are the same, you end up having a linear molecule with no net dipole. So that's an example of where you have lone pairs of electrons, but you end up having a nonpolar molecule. The other one is where we had AX4E2, which was called square planar. The square planar arrangement had 2 lone pairs equally pulling above and below the planar molecule. And so just like before, if all these outer atoms are the same, they all lie within a plane to one another, and so they're 90 degrees apart, and their net dipoles will cancel each other out. And so the shape is perfectly symmetrical, and you'll end up having a nonpolar molecule. Now let's look at 3 organic molecules, each of what we'll learn individually in separate chapters in this class and study more in depth. But for now, we're just going to compare their bond lengths and their bond energies. So ethane, which is alkane, has the Lewis structure like this. We have C2H6 as our formula, and it has all single bonds contained within it. So that is an alkane, which is actually the type of organic molecules we'll learn first. Next, let's compare that with ethylene, which is also called ethene. This is a group of molecules called an alkene. So we went from alkane to alkene, and we have carbon-carbon double bond here. And we have 2 single bonds to hydrogen on each side. And so the formula for ethylene is C2H4. And then lastly, Let's move on to something called acetylene, which is kind of the short name. Ethine is the formal name. And in this one, we have a carbon-carbon triple bond. And each carbon has a single bond to hydrogen. So the formula would be C2H2. And that's a class of molecules called alkynes. So we have alkanes, alkenes, and alkynes. And we'll look at all of them separately, all of their reactions, their properties, how we go about naming them. But for now, let's compare the bond length. As we go from an alkane, which the carbon-carbon bond is single in an alkane, the length is 1.54 angstroms. Then when we move to an alkene where we have a carbon-carbon double bond, the length is 1.34 angstroms. So it's getting shorter. That means those electrons in a double bond are being held tighter together than they are in a single bond. And then in our alkyne where we've got a triple bond, our carbon-carbon bond length is 1.2 angstroms. So it got even shorter. So there's this trend as we go from a single to a double to a triple bond that the bond length is getting shorter. And now let's compare that to the bond energy. So our bond energy is essentially, you can think about it, how much energy it would take to break that bond. So the bond energy for our alkane is 368 kilojoules per mole. And we're specifically looking at the carbon-carbon bond in this case. Versus our double bond, would take 632 kilojoules per mole to break our double bond, our carbon-carbon double bond. So it's a stronger bond. And our triple bond would take 820 kilojoules per mole to break. So that's the strongest bond that we have there. So it's an inverse trend here. As we go from single to double to triple bonds, the bonds are getting stronger in this case. So our strongest bond is our triple bond, and then our double bond, and then our single bond. So it's hardest to essentially break that triple bond because it's much stronger. It has much more bond energy contained within it. Next, we'll review a concept called formal charge, which will be fairly important when analyzing organic structures. So formal charge is a charge that we assign to an atom in a molecule. And it's kind of a bookkeeping method where we are assuming that the electrons and the bonds between them are shared equally. And we kind of break those bonds down the middle and give each atom one of the electrons. But we're assuming that they're shared equally when we use the formal charge method. Atoms in the molecules, they can have an unbalanced charge. And so we have to analyze it because depending upon which atom the charge lies on, it can affect the molecule's stability. To calculate the formal charge of an atom, what we're going to do is compare the number of valence electrons that that atom should have compared to what the number of valence electrons that it actually has. So when we say electrons it should have, I mean from the group number on the periodic table. So how many valence electrons should a nitrogen atom have? Well, nitrogen's in group 5A, so it should have 5 around it. And then how many electrons it actually has, that'll come from the Lewis structure that we're analyzing. All right, so let's try an example. Determine the formal charge on each atom in the following structures, and then we'll compare the two structures and decide what one is the better Lewis structure. So both of these are technically accurate Lewis structures because everyone's happy, everyone has an octet, none of the rules are broken. So that's where formal charge steps in, is like, okay, what one is more appropriate? So what my method is I break the bonds in half, so we're drawing this imaginary line through them, and one electron gets associated with each atom. And so then we count the electrons around them and compare them with the number they should have from the periodic table, essentially. So hydrogen's in group 1A, so it should have 1. And in our drawing, hydrogen does have just 1 electron around it. So it would be 1 minus 1, and we have a formal charge of 0. Oxygen is in group 6A, and in our structure on the top here, we have 2, 4, 5, 6 electrons. So we're going to have 6 minus 6, or 0 formal charge. bromine is in group 7A, so 7 valence electrons. And in our structure here, we have 2, 4, 5, 6. So we're going to have 7 minus 6, which is plus 1. And our outer oxygen would be 6 minus, we have 2, 4, 6, 7, or negative 1 formal charge. So in the top molecule, we do have 2 atoms with a 0 formal charge, and our bromine has a plus 1, and bromine's quite electronegative, so it's not really great for it to have a positive formal charge. And then our outer oxygen has a negative 1 formal charge. Now let's compare that with the lower structure. Hydrogen's still going to be 1 minus 1, which is 0 formal charge. The oxygen below here is the same. It still has 6 electrons associated with it, so it has a 0 formal charge. But now our bromine and our oxygen will be different. So bromine has 7 minus 2, 4, 6, 7 in this structure. So 0 formal charge. And our oxygen will be 6 minus, we got 2, 4, 6 electrons associated with it. So 0. So our bottom structure is considered our better Lewis structure, or the best one comparing these two, because it has minimized the amount of formal charge on the atoms. We were able to draw a structure where there is no formal charge on any of our atoms. So that one's considered our better one between the two of these. Let's do one more example where we calculate the formal charge on each atom. So in our first one, we're going to break those bonds. So we're going to assign an electron to each side and then count them up and compare them with the periodic table. So each hydrogen has 1 electron, so for each hydrogen, it's going to be 1 minus 1, so they all have a 0 formal charge. For our oxygen, it's in group 6A, so it'll be 6 minus, we got 1, 2, 3, 4, 5 electrons around it. 6 minus 5 is plus 1. So our oxygen has a positive 1 formal charge, and the hydronium ion. Next, this is formaldehyde, which is an organic compound, and we're going to break those bonds. So we got 1 electron going to each side, and in the double bond, 2 electrons going to each side. Hydrogen has 1, so it's going to be 1 minus 1, 0 formal charge on hydrogen. Carbon is in group 4A, and so our carbon is going to be 4 minus, we got 1, 2, 3, 4 electrons, 4 minus 4, 0 formal charge. Oxygen is in group 6A, so we got 6 minus 2, 4, 6 electrons. So 0 formal charge on every atom in the middle molecule. And then on our last one, which is O3, it's called ozone. Let's break our bonds. We're going to have 1 electron here, 1 here, 2 here, and 2 here. So starting on the oxygen on the left, we're going to have 6 minus, we got 2, 4, 6, and then 1 there, 7. So 6 minus 7, that oxygen is a negative 1 formal charge. The oxygen in the middle is going to be 6 minus, we got 2, 4, 5, positive 1. And the oxygen on the right-hand side is going to be 6 minus, we got 2, 4, 6 electrons. So 0 formal charge. So for our ozone molecule, we got a negative 1, a plus 1, and a 0. When you're drawing organic molecules, you're pretty much dealing with a lot of the same elements over and over again, especially since most of them are covalently bonded. So you're going to be dealing with a whole bunch of non-metals in the upper right corner of the periodic table. Something that can help you kind of look at a molecule and assess it quickly is its valency. So there are molecules that like to form the same number of bonds. So in this scenario, we're pretending that they're all single bonds, but if they deviate from the number of bonds that they like to form, then there will be a formal charge. If they form the bonds that are listed below, then the formal charge will be 0. And you can get used to this and kind of quickly look at a molecule and know if it's going to have a formal charge or not. So, for example, carbon is called tetravalent. Carbon likes to form 4 bonds. In this little picture example, it's showing it with 4 single bonds, but it could be 2 double bonds, it could be a triple bond and a single bond. So any way that it can make 4 bonds. If it has 4 bonds, it will have a formal charge of 0. Nitrogen is trivalent. That means it generally forms 3 bonds. So usually you'll see nitrogen with 3 single bonds, and there's an unwritten lone pair of electrons on there. If you see that, then the formal charge on nitrogen is 0. Oxygen is called divalent. It generally forms 2 bonds, and what's unwritten is that there's 2 lone pairs of electrons on oxygen, completing its octet. So when you see that, the formal charge on oxygen is 0. And monovalent atoms that are important are halogens and hydrogen. So hydrogen always forms 1 bond, and the halogens like to form 1 bond as well. So fluoro, chloro, bromo, or iodo groups, where X represents a halogen generically, you will see them with usually 1 bond, and then that means they have no formal charge or a formal charge of 0 associated with them. So knowing these common valencies can help you to more quickly draw Lewis structures and more quickly analyze Lewis structures. 2 important things to know about a molecule are its molecular geometry, which tells us its shape. And when we talk about the shape of it, we're thinking about things like, what is the bond angle between the atoms? Maybe what is the bond length between 2 atoms? So bond angle and bond length are really important to analyze when you think about the different shapes. And you might remember that we kind of looked at what some common bond angles were for different geometries when we took Gen Chem. So these are important things to kind of review and know before essentially analyzing how a reaction happens. For example, with water, we would have classified that as an AX2E2 type molecule, which the molecular geometry for that class was called bent. And we would have learned that the bond angle for something like water for a bent molecule was about 104.5 degrees between the hydrogen, oxygen, hydrogen. So that's the type of stuff that we want to think about. And those geometries, those bond angles, came from when we learned VSEPR. And we'll kind of review a little bit of the basics of VSEPR in a few slides. Sometimes when we're analyzing reactions, the important thing to assess is the bond length. And bond length is essentially the distance between the centers of the 2 nuclei of the atoms that are bonded together. So when we look at bond length, the things that really impact it are the size of the atoms that are bonded together and the electronegativity of the atoms that are bonded together. So if we compare methane, which is CH4, ammonia, which is NH3, and water, H2O, carbon, nitrogen, and oxygen are all in the same period or the same row of the periodic table. So we'll start there with those 3. Notice what's happening to the bond length between our hydrogen and the atom that's changing. So hydrogen remains the same, which allows us to compare the length here. So hydrogen to carbon, 1.09. Hydrogen to nitrogen, 1.00. Hydrogen to oxygen, 0.958. So as we go from carbon to nitrogen to oxygen, the bond length is decreasing. And why is it decreasing? What's happening as we go from left to right across the given period? It's decreasing due to the fact that our electronegativity of those atoms is increasing. So carbon is less electronegative than nitrogen, and nitrogen is less electronegative than oxygen. So remember, electronegativity tells you how greedy a certain atom is for electrons in a covalent bond. So oxygen has a much higher pull for those electrons, so you end up having a little bit of a shorter bond length than compared to nitrogen. And carbon is less electron greedy than nitrogen, so the bond length is a little bit longer compared to that. So the bond length is inversely proportional to the electronegativity when we're in that same row of the periodic table. Now if we compare our water with our hydrogen sulfide, you'll notice that sulfur is right below oxygen on the periodic table. So those 2 are not in the same period, but they are in the same family, or in other words, the same group. So now we're not going to compare electronegativity. we're going to compare the atom size. So atomic size becomes the overriding factor when you're changing the family that you're in. Sulfur is a much larger atom than oxygen is. Oxygen's smaller. And so really the size of that atom impacts the bond length. If sulfur is much bigger than oxygen, notice the distance between the hydrogen and the sulfur, 1.35 angstroms compared to the oxygen-hydrogen bond length, 0.958 angstroms. So that size makes a big impact on the distance between those two, or essentially the bond length. So those are the two kind of trends that you want to be familiar with throughout the periodic table. Atomic size is when you're dealing with the same group or family, and electronegativity is when you're dealing with the same row or period on the periodic table. And we actually already saw this a little bit ago, but the bond order, or in other words, if it's a single versus double versus triple bond, also had an impact on the bond length. Bond order of 1 would represent a single bond, a bond order of 2 would represent a double bond, and a bond order of 3 would represent a triple bond. So the single bond is the longest, then in the middle we have the double bond, and the shortest is the triple bond. Next, we'll review the part of the VSEPR table that's probably most important for this class. We don't need to know the whole table, but AX2, AX3, and AX4 families are going to be what you see most when dealing with organic chemistry. So AX2 was where we had two outer atoms bonded to a central atom, and the molecular geometry was called linear, and our structure picture was this, and the bond angles were 180 degrees. The hybridization of the central atom, which in these pictures would be atom A, was sp hybridized. We'll review hybridization a little bit later. The next main family is called AX3, and there's two that live within that family. You can have AX3 where you have 3 atoms that are bonded to that central atom. So this would be our picture. The name of that shape is called trigonal planar, and the bond angles are all 120 degrees apart. Or you could have a situation where you have 2 atoms bonded and you have 1 lone pair. That's called AX2E. So in that case, we have 2 outer atoms and we have 1 lone pair of electrons on the central atom. The name of that shape is called bent. The exact bond angles aren't important, but what we know is that the lone pair of electrons pushes down on the bonding pair and shrinks the bond angle a little bit. So it becomes a bit less than 120. The hybridization of our A central atom and our AX3 family is sp2 hybridized. And then the last important one is the AX4 family. And then there's 3 subclasses within that family. AX4 is called tetrahedral, and that's when you have 4 outer atoms bonded to that central atom. The bond angles are 109.5 degrees. If we have AX3E, where one of the bonding pairs has been replaced with a lone pair, we're going to have this situation. We have 3 outer bonding pairs, 1 lone pair, and that's called trigonal pyramidal because the shape kind of resembles a pyramid. And just like before that, lone pair pushes down on the bonding pairs and shrinks the angles a little bit. So for the example of something like ammonia, NH3, the bond angles are about 107.3 degrees, so a bit less than 109.5. The last family is AX2E2, where we have 2 bonding pairs and 2 lone pairs. So 2 bonding pairs, 2 lone pairs on the central atom, and that is also called bent. So these two actually have the same name for their molecular shape, but they have different bond angles. So now we have 2 lone pairs of electrons that are pushing down on our bonding ones. So it gets even less than 109.5. It shrinks down even more. A molecule that this would be an example of is something like water, H2O. So the bond angles are even less than 109.5. For water, they're around 104.5. Anybody that lives in that family, the AX4 family, is going to have hybridization on the central atom of sp3. So when we're talking about VSEPR theory and we're thinking about how many domains, or sometimes it's called steric number, there are around a central atom in order to determine its family, we're counting the lone pairs and the number of bonding pairs. So in something like methane, we have 4 bonding pairs and no lone pairs. So this would be an example of AX4. In something like ammonia, we have 3 bonding pairs, but we also have a lone pair of electrons on there. So how we label the lone pair of electrons is using the E notation in the AX method. So this would be AX3, X is 3 bonding pairs, and then E. So our first one was tetrahedral, and our second one, ammonia, is going to be trigonal pyramidal in shape. And then lastly, for H2O, we have 2 bonding pairs, and then we have 2 lone pairs. So we would represent that as AX2E2, and that's going to be the shape bent. But notice all 3 of these are considered to be within the same family. So they're all derived from the tetrahedral arrangement because they all have the same steric number, which is 4, the total number of things around it. Some books call it the electron cloud number, the number of electron domains, steric number. All those mean the same thing. How many things total are there around your central atom? And if you add up the number of X's and the number of E's, they all add up to 4. Let's try a couple of practice examples here. And some of this is just going to come from you reviewing VSEPR and reviewing the names of the geometries and hybridization. But let's just go through these now. We want to say, what is the hybridization of that central atom? And then what is the name of the shape that that molecule has? So in our first one, we have AX3E. So AX3E, that's going to be derived from the tetrahedral family, and we said that that was called trigonal pyramidal. And since it's from the tetrahedral family, the hybridization on that central atom is going to be sp3. For our next one, we're looking at the central atom, and we have 1 domain, 2, 3 things around our central atom. It doesn't matter that the carbon has a double bond to oxygen. Oxygen is still just 1 atom attached to the central atom. So this would be an example of AX3. And this is called trigonal planar because the molecule is planar and it's flat. When you're in the AX3 family, the hybridization is going to be sp2 on the central atom. Moving on to the right, here we have AX2E. We have 1 atom, 2 atoms, and then we have a lone pair on the central atom. So the shape of this molecule is going to be called bent. And our hybridization, well, AX2E belongs to the AX3 family, so it's going to be the same as the last one. We have sp2 as the hybridization. And then our next one on the lower left, we have 2 carbons that we're going to indicate the hybridization for. And we could talk about 2 different shapes for each of them. So for the carbon that I'm circling first on the left, that carbon has 4 domains around it. We have 3 hydrogens, and then it's singly bonded to another carbon. So that carbon would be AX4, which is tetrahedral. And the hybridization for that carbon specifically would be sp3. Now for the carbon that has a triple bond, we'll look at that one separately. That carbon has 1 domain, which is that carbon attached to it, and then it has another electron domain attached to it. It has 2 things. So that would be an example of AX2, which is linear. So 180-degree bond angle for a linear molecule. And the hybridization in that case will be sp. And last molecule on the right, we have a carbon that has a double bond. So the number of things around that is 1, 2, and then 3. We could have looked at the other carbon, but the molecule is symmetrical. So we have AX3, which we already said was trigonal planar. And so the hybridization of that carbon will be sp2. Notice that a carbon that has all single bonds, such as the one in the lower left, is sp3 hybridized. A carbon that has a double bond is sp2 hybridized, and then a carbon with a triple bond is sp hybridized. One other thing that you'll come across, and we will talk about more in depth when we learn stereochemistry, is something called the wedge and dash notation. If you do see it for now, all I really care that you understand at this point is that a wedge being drawn is trying to indicate that that atom is pointing out of the page towards you, whereas a dash being drawn is indicating that that atom, that bond, is pointing back away from you. So using wedge and dash structure is just trying to indicate that 3D structure a little bit better as someone is drawing it on 2D paper. And then when they use straight lines, no wedge or dash, those are considered to be in the plane of the paper. So those flat lines are in the plane, a wedge is coming out of the page towards you, and a dash is going behind the page away from you. So this is really common to draw for drawing something like methane, which has tetrahedral arrangement, because we know that when we draw it flat like this, the molecule does not really look like this. There's not 4 carbon-hydrogen bonds just laying flat in the plane of the paper. It's got that tetrahedral geometry, 109.5 degree bond angle. So using wedge and dash is just an easier way to represent that and kind of get across the real shape of it, the molecule. You also might recall learning about resonance structures, and later on we're going to talk about resonance structures in a whole new way, but for now we should just review the basics of what they are and what you would have already seen in general chemistry. So sometimes when you draw a Lewis structure, one single Lewis structure does not really accurately depict the full picture, and so we draw these hybrid structures, which kind of there could be multiple of, and they give an overall more accurate depiction of what the real molecular structure is. So an important thing to realize is that resonance structures are not in equilibrium, they're not changing back and forth between each other, but they are a hybrid of an overall structure for that molecule. So when a molecule has resonance hybrids, it's considered to be more stable. Resonance stabilizes a molecule, and so when a molecule has that, it's a good thing. We call it resonance stabilized. So an example of this that you would have seen before is something like with the carbonate ion. Carbonate is CO3 2-, and so we could have went through all of our rules and drawn the Lewis structure, and we would have came up with a picture on the left, let's say. We would have had to move a lone pair on oxygen and create a double bond. And we don't always draw resonance structures, but if we're trying to think about resonance, it is important that we do. Also notice the brackets and the charge on the outside because we do have an ion. The next thing we would do is say, well, is that double bond really right there in the lower left? Like, is that the only place that we would really find a double bond in the carbonate ion? And the answer is no, it's not just there. So we draw resonance arrows, which are double-headed arrows that go between the resonance structures, and then we move around the location of that double or triple bond. We move around those electron pairs. So no, the electrons don't have to live in the lower left. We move them now to the top, so they could be there. And then they could also be in the lower right, so we would need another resonance arrow, and then we would throw that double bond in the lower right as well. So all 3 of these are resonance structures. So for carbonate, we have 3 total structures in order to show the total resonance hybrid. And it's important to also realize that carbonate really does not have 1 double bond and 2 single bonds. It has 3 equal bonds, but we are depicting it this way because this is the only way that we can really show it on paper. There's really 3 equal bonds, and they're all about 1.33 bonds if we were to think about the bond order. So resonance structures are not changing between these. The electron pair really isn't just jumping around to those locations, but this is the best way that we can represent that the molecular structure is a combination of between a single and between a double bond for all 3 carbon-oxygen bonds, and they're all actually equal.